new topic, vector space. We have studied vector in physics. We probably used to define forces in vector space. We will use the vector space in mathematics. In mathematics, vector used to define two operations, addition and scalar multiplication. Now, generalized of these two operations means addition and scalar multiplication is the vector space, which is all be vector, all element here vector. Sometimes this vector space is called as linear space. In vector space, you can have two-dimensional vector space, which is probably plane. This is one vector. If we add this other vector, consider this is u and this is v, then u plus v would be other vector. Okay? And you can scale this vector. This would be cu. Okay? 3 dimension, this is look like a space. You can see also 4 dimensional vector space, 5 dimensional vector space, n dimensional vector space. This is different type of vector space, but this is the linear algebra. In vector space, V equal to set whose elements are vectors, and F equal to set of numbers which is called here scalars. Here the notation is V, which is vector space, and F, which is associated with field, and this space associated with two operations, addition and multiplication. Consider U, V, W are vectors in V, and K and C are real numbers. Space here 5 addition axiom. U plus V here always belongs to this vector space. That means this is the closure under addition, and here U plus V equal to V plus U. That means here the operation is commutative, and here U plus V plus W equal to U plus V plus W. That means this operation is associative, and V has additive identity 0. That means V plus 0 equal to V, and for every V belongs to V, there is an additive inverse minus V such that V plus minus V equal to, here the additive identity is 0. Next property is properties of scalar. First property, closure under scalar multiplication. You can multiply the vector with any scalar, then this would be member of vector space. Next property is distributive property. At first, add two vector and multiply with one scalar, then this would be k times u plus k times v. These are similar. Third property, at first add two scalar, then multiply with one vector. This is also similar to k times u plus c times v. Okay. Next property, at first you scale two number, then multiply with vector. At first scale one vector, then multiply with one scalar. This is similar, and this property is called associative property. Or 1 be the multiplicative identity, because 1 times u, here the u. This is actually the scalar identity, and here does not have any multiplicative inverse. In vector space, only multiplicative inverse has in addition. Now let's see couple of example of vector space. First example, Fn, where F be any field with usual operation addition and scalar multiplication always be vector space. This is one example. Next example, F infinity, which is defined as set of all sequence of element of the field, any field F. Obviously, this is also example of vector space because here F infinity is defined as x1, x2, so on, where xj belongs to A, where j equal to 1, 2 up to so on. And this is the vector space because here the addition and scalar multiplication are defined as x1, x2 up to dot dot plus y1, y2 up to so on. This would be x1 plus y1, x2 plus y2, so on. Also, lambda times x1, x2 would be equal to lambda x1, lambda x2, so on. So, obviously, set of all sequences whose each term be the member of any field. So, this is obviously example of vector space. Example, consider S is a set and F has denoted the set of all function S to F. Here F is any field similar to before. Obviously, this is also example of vector space because if you consider two function fg belongs to fs, then their sum is also belongs to this set. And the function is defined by f plus gx equal to fx plus gx. Also, for all lambda belongs to f and f belongs to fx, then lambda times f also belongs to this set because here the function is defined as lambda fx equal to lambda times fx, where for all x belongs to the set S. Are you getting the meaning? OL. Next example. M cross n matrices whose entries any field. Here, obviously, addition and scalar multiplication always will be defined. Here, each element of the matrices are vectors. That means vector does not mean any object on the plane or space. This can be anything. We will do more generalized of vector space. This can be any polynomial, matrices, functions, also solution of differential equation, so on. Next example, PNR, which is equal to the set of all polynomial in real variable t with degree of polynomial not exceeding n. This is easy type of example. This is also vector space. Here, multiplication, scalar multiplication always will be satisfied because consider two polynomial in PNR such that p equal to p naught plus p1 to p on t plus p2t square up to pnt to the power n and q equal to q naught plus q1t plus q2t square plus up to qnt to the power n, where here t belongs to real number. Here p and q as a vector, where p is a set of polynomial of degree n and q is a set of polynomial of degree n. Are you getting? Then p plus q also belongs to this vector space because this is also polynomial whose degree is n and the variable is real variable. Alpha times p also would be alpha p naught plus alpha p1 to up to alpha p to the power n tn. This is also be the set of polynomial of real variable t with degree n. So this is also be member of this vector space. So this is example of vector space. Are you getting? OL. Next example, AB set of all m cross n matrices. Here the space is defined as x belongs to Rn such that Ax equal to 0. That means here X stands for any vector who is standing only the column vector. Here the solution is Ax equal to 0. That means here the 0 means only m vectors. And obviously this is subset of Rn. Since this is subset of Rn, so obviously this is vector space. And here obviously A times x plus y would be Ax plus Ay, which would be 0. So alpha times x, which is equal to 0. That means all condition of vector space has satisfied here. So this solution is actually called as null space, which I will study in my next lecture. What is the null space? Obviously will be vector space. Our next example, consider C of AB, which is defined as set of all real valued continuous function over the closed interval AB. This is obviously be vector space, because if you consider two continuous function and P and Q belongs to C of AB, then defined as P plus Qt equal to Pt plus Qt and alpha Pt equal to alpha times Pt, where for all alpha belongs to R. This is obviously be vector space, and this is the real vector space. And if you change the field here, if you change here the complex field, then this function would be complex vector space. Are you getting? Well, then CKAB means the set of all real valued function of A with the property here the kth derivative is continuous on the interval AB. Obviously this is same like before, this is vector space. Here vector addition and scalar multiplication would be as before. So set of all real valued continuous function which is defined as CKAB with the property here kth derivative is always continuous of this function. So here this function is defined as CKAB, always be real vector space. Are you getting? Similarly, infinity AB, that means set of all functions that are infinitely many times differentiable in the open interval AB. This is similar type of question, so this is obviously be vector space. Our next example, consider f of AB to R. This is the set of all function which is defined from AB to R. And here the vector space is defined as set of all function such that integration a to b ft dt exists. That means set of those function which is Riemann integral. Obviously this is vector space, because if we consider two function which is Riemann integrable, then their sum obviously would be Riemann integrable. And if we multiply any function which is Riemann integrable with a scalar number, then obviously this is also Riemann integrable. So this is member of vector space. So obviously set of all function which is Riemann integrable, obviously this is be a vector space. Let's see other type of example. Consider L of y equal to set of all differentiable equation of n degree. This is dny over dt to the power n plus a1 dn minus y over dt on n minus 1 plus a2 dn minus 2 y over dt n minus 2 up to a n yt. Here the vector space is defined as set of those y such that solution of this differential equation. This is actually the L of y equal to 0. And obviously this is vector space similar to before. Another example. In 3D plane, consider this plane. Now my question, is this possible to vector space if you consider only this plane? At first just think. If you consider in this plane this vector, then minus of this vector would be this plane, but this plane not belongs to our defined space. So if we consider this plane, then this plane not be vector space. But if we consider the line which is passing through origin, then this would be always vector space, because all rules of vector space here will be valid. Means if you take any partial part of the space, then this would be not vector space. But if you take any line which is passing through origin or any plane which is passing through origin, this would be vector space. If we consider those set x belongs to R3 such that x2 equal to alpha x1, where alpha be any fixed number, that means set of those line which is passing through origin, obviously this is vector space. Similarly, if we consider set of those plane which passes through origin, this is obviously vector space. This will satisfy all axiom of vector space. As for example, consider V equal to x belongs to R3 such that x1 plus 2x2 plus 5x3 equal to 0. This is obviously would be vector space. Let's see some couple of examples. Here, vector space obviously Rn, but the field over R. Then Rn over the field R, obviously this is vector space. Similarly, if we consider the complex number Cn over the field complex, this is also vector space. Similarly, Cn over the field R, this is also vector space. But if we consider the vector Rn over the field's complex number, this is not vector space, because if we consider a vector from Rn and if we multiply with a scalar complex number, because if you take any arbitrary vector from Rn and multiply with any scalar, that means one complex number, then this not belongs to Rn. This is member of complex number. So this is not a vector space. Are you getting why in any space why field theory is more important? If you don't see my field theories video, at first I will highly recommend you, please see at first the video I had seen few minutes ago. Polynomials degree less than or equal to n be vector space. But if we consider polynomial of degree n, then this not be vector space. This is vector space because here consider less than equal to. How? Check it. For easy calculation, consider polynomial of degree 2. Here this is not closed under addition, because consider 2 second degree polynomial. This is consider this is f and consider this is g. Then their sum would be 4x minus 2, which is not the second degree polynomial. So this is not belongs to the vector space, which is denoted as polynomial of degree 2. Are you getting why I have told you polynomial of degree n not be vector space? If we consider polynomial degree less than equal to 2, then this would be vector space. But if we consider the polynomial of degree n, then this is not vector space. So, polynomial of degree less than or equal to n always be vector space. Okay? Well, today I will stop here. In my next video, I will discuss vector subspace. But at first, I will highly recommend you. Please see today's video with pay attention. See you soon. Stay safe and stay positive always.